Rub a balloon against your hair and it can stick to a wall. Walk across a carpet and touch a metal handle, and a tiny spark may jump from your finger. We call the invisible property behind these effects electric charge. But what is that charge actually made of? An electron carries negative charge, while a proton carries positive charge. So is charge some hidden substance stored inside particles? Is it made of smaller particles? Is it created by photons, energy, or perhaps the Higgs field? Quantum physics gives us a very different picture. At the deepest level we have tested, electric charge does not appear to be a material ingredient at all. Instead, it behaves like a fundamental quantum property connected to fields, interactions, and symmetry. To understand that answer, we have to begin with a simple mistake almost everyone makes when first thinking about electricity. When we hear the word charge, it is natural to imagine something being carried from one place to another. We charge a battery. We charge a phone. We say that an object becomes electrically charged after gaining or losing electrons. This language is useful, but it can also mislead us. It makes electric charge sound like a liquid, powder, fuel, or invisible material that particles store inside themselves. Modern physics does not describe it that way. An electron is a particle, but its electric charge is a property of that particle. The distinction is important. An electron also has mass and spin. We do not imagine that its mass is a collection of tiny mass particles sitting inside it. We also do not imagine that its quantum spin is produced by a miniature wheel physically rotating inside the electron. These properties are part of the way the electron is described by the laws of physics. Electric charge belongs to the same broad category. It tells us something fundamental about how the electron behaves and interacts. When physicists say that an electron has negative electric charge, they are not claiming that a small amount of negative material has been packed inside the electron. They are saying that the electron responds to electromagnetic fields in a particular way. Put an electron in an electric field and its motion changes. Put a positively charged particle in the same field and it responds in the opposite direction. The words positive and negative therefore describe a relationship. They are not labels for two mysterious substances. The signs could even have been named the other way around. What matters physically is that the two types of charge behave oppositely. This immediately separates electric charge from ordinary material ingredients. 2 drops of water can contain different amounts of water. 2 stones can contain different amounts of matter. But every electron we observe behaves as though it carries the same basic electric charge. One electron does not normally possess 90% of the standard electron charge while another contains 110%. Electrons are remarkably identical in this respect. That makes much more sense if charge is part of what defines the electron rather than an arbitrary amount of substance stored inside it. This also explains why saying that charge is made of electrons is not quite correct. Electrons can transport electric charge, especially in metals, but electrons are not electric charge itself. Many other particles are electrically charged. Muons carry negative charge. Positrons carry positive charge. Quarks carry fractional electric charges. The W bosons are electrically charged as well. A proton carries positive charge even though it is not an electron and has a completely different internal structure. At the same time, some particles are electrically neutral. Photons are neutral. Neutrinos are neutral in the Standard Model. Neutrons have zero net electric charge even though they contain charged quarks. So electric charge cannot simply mean electron material. It is a more general property shared by very different quantum systems. Even the familiar numerical value of the elementary charge can be misunderstood. In the modern system of units, the magnitude of the elementary charge is exactly defined as $1.6021766634 times 10 carat minus 19 coulomb. That exact number belongs partly to the way humans define the coulomb. Nature does not carry around a label with that number. The deeper physical question is why the electron has 1 unit of negative charge while other particles have the values they do. Why is a proton opposite in charge to an electron? Why do quarks have charges of 2/3 or minus 1/3 of the same basic unit? Why are neutral atoms possible? Those questions take us beyond measurement and toward the structure of quantum theory. Before quantum physics, charge could be pictured as something attached to a small particle. But the modern picture changes what we mean by the particle itself. An electron is not simply a microscopic ball moving through empty space. In quantum field theory, the electron is associated with an electron field that exists throughout space. What we call an electron is a quantum excitation of that field. Once we move to that description, asking what charge is made of becomes less like opening a box and more like asking why that quantum field interacts with electromagnetism in the way it does. That is where the real investigation begins. Charge is certainly measurable. Its effects are real. It controls forces, scattering, atomic structure, chemistry, electronics, light emission, and much of the visible universe around us. But being real does not require being made of smaller pieces. According to our best-tested theories, charge may be real because it is built into the rules governing quantum fields themselves. To understand that idea, we first need to replace the familiar image of the electron as a tiny charged marble with something much stranger. Most pictures of atoms show electrons as tiny spheres moving around a nucleus. Those diagrams are useful for teaching basic ideas, but they should not be mistaken for literal photographs of atomic reality. Modern particle physics describes an electron using quantum field theory. In this framework, the fundamental objects are fields, and what we call particles appear as quantized excitations of those fields. There is an electron field. There are quark fields. There is an electromagnetic field. There are fields associated with neutrinos, gluons, the Higgs boson, and the other particles of the Standard Model. An electron is therefore not best imagined as a tiny solid object containing smaller compartments. It is a quantum excitation of the electron field. That matters enormously for the question of charge. If the electron were a miniature container, we could imagine opening it and looking for whatever material produces its negative charge. But the Standard Model does not provide us with known smaller objects inside the electron. In fact, the latest high-precision measurements from the ACME experiment confirm the electron's charge distribution is perfectly spherical to an astonishing degree, showing no evidence of internal structure. As far as the Standard Model is concerned, it is elementary. That means its electric charge cannot currently be explained by adding together charges belonging to smaller electron constituents. Compare this with the proton. A proton is not elementary. It is a bound state governed by quantum chromodynamics. Its internal structure involves quarks, gluons, and a constantly interacting quantum environment. Because the proton is composite, we can meaningfully ask how the charges of its quark degrees of freedom combine to produce its total positive charge. The electron is different. We have no confirmed smaller constituents whose charges add together to make -1 elementary unit. Its electric charge is instead built into the way the electron field participates in the electromagnetic interaction. Imagine trying to remove the charge from an electron while leaving the rest of the theory unchanged. We cannot simply drain something out of it. We would have to modify the mathematical description of the electron field and change the way that field couples to electromagnetism. A neutral version of the electron would behave very differently. It would not form ordinary atoms in the same way. Chemistry would radically alter. Electrical conduction would change beyond recognition. The very structure of matter would be transformed. This shows that charge is not an optional coating added to the electron. It is deeply tied to the electron's identity within the Standard Model. The field picture also helps explain why all electrons appear identical. If every electron is an excitation of the same underlying electron field, then we should not expect each electron to come with a separately manufactured internal configuration. They are manifestations of one quantum field and therefore share the same defining properties. This is one of the reasons particle physics treats identical elementary particles so differently from ordinary objects. Two baseballs can differ because each one contains a different arrangement of atoms. Two electrons cannot be distinguished by saying one contains slightly more electron material than another. Quantum theory does not allow us to label them in that classical way. Their sameness is fundamental to the theory. The same reasoning applies to their charge. Each electron carries the same electromagnetic quantum number. The word carries can still make it sound as though the charge is sitting inside the particle, but a more accurate statement is that the electron field has a specific electromagnetic charge assignment. That assignment determines how it interacts with the electromagnetic field. This also tells us why the electromagnetic field itself should not be confused with the charge. A charged particle can create and respond to electromagnetic fields, But the field surrounding it is not simply the charge spread out through space. The electromagnetic field has its own dynamics. It can carry energy and momentum. Its quantum excitation is the photon. Charge plays a different role. Charge determines how matter fields source and interact with that electromagnetic field. At this point, the language becomes more abstract, but the physics becomes more precise. We stop asking where the negative substance is hidden and begin asking how the electron field transforms under a particular symmetry. That symmetry is associated with electromagnetism. Physicists call it a $1 gauge symmetry. The phrase sounds mathematical because it is mathematical, but its consequences are physical. It controls which interactions are allowed and how charged fields behave. The electron's charge is connected to the way the electron field participates in this symmetry. This is why quantum physics does not answer the charge question by pointing to another tiny particle inside the electron. It answers by revealing a deeper organizational principle. The electron is an excitation of a field. Its charge is one of the properties defining how that field fits into the electromagnetic structure of nature. To make sense of that statement, we now have to look at what physicists mean when they call charge a quantum number. In quantum physics, a particle is described by more than its position or motion. It belongs to a mathematical structure containing properties that determine how it behaves under different transformations and interactions. Physicists often summarize some of these properties using quantum numbers. Electric charge is one of the most important. Calling charge a quantum number does not mean it is imaginary or merely a convenient label. The number corresponds to real physical behavior. An electron bends one way in a magnetic field, while a positron bends the opposite way. Charged particles respond to electric fields. They interact with photons. They influence atomic energy levels and chemical bonds. The number assigned to electric charge tells us how these interactions occur. To understand why symmetry enters the story, we need to talk briefly about phase. Quantum states can involve complex numbers, and complex numbers contain a phase. You can loosely imagine that phase as an angle, although the full mathematics is richer than a clock hand turning around a circle. Certain changes of phase leave observable predictions unchanged. The symmetry associated with these phase rotations is mathematically described by a group called $1. Electromagnetism is connected to such a $1 gauge symmetry. A charged field transforms under this symmetry in a way determined by its electric charge. In simple terms, the charge tells us how strongly the field's phase responds to the electromagnetic transformation. This may sound far removed from the spark that jumps from your finger to a metal doorknob, but the two descriptions are connected. The spark is a large-scale consequence of countless charged particles obeying these underlying quantum rules. The electron's negative charge means that its field has a specific transformation property and a specific coupling to the electromagnetic field. The positron has the opposite charge, so its transformation and coupling differ by sign. An up quark has a different electric charge again. The charge is therefore not an extra object riding along with the particle. It is part of the mathematical identity of the field. One reason this description feels uncomfortable is that people often want a physical property to be explained by a visible mechanism. If we ask what makes a clock tick, we can open it and find gears or electronics. If we ask what gives a planet its mass, we can trace much of that mass to the energy and matter composing it. But a fundamental quantum property may not work that way. Physics may eventually explain the property through a deeper theory, but that deeper theory does not necessarily have to involve smaller material pieces. It might explain why certain symmetry structures are possible and why certain quantum numbers must take specific values. This distinction between composition and explanation is essential. A charge can be fundamental without being mysterious in every respect. We know how to measure it. We know how it enters the equations. We know how it affects interactions. We know that different particles carry different charge values. The mystery is why nature selected the entire pattern. Negative charge itself should also not be interpreted too literally. There is nothing physically negative about an electron in the everyday sense. The sign is conventional. Long ago, humans chose which kind of electrical behavior to call positive and which to call negative. We could have reversed the names. What cannot be changed is the relative behavior. Like charges repel in ordinary electrostatic situations, and opposite charges attract. The direction of electromagnetic response depends on the sign. So positive and negative are relational labels within a consistent structure. The magnitude also matters. An electron has 1 unit of negative elementary charge. An up quark carries plus 2/3 of that unit. A down quark carries minus 1/3. These values are not explained by saying that a particle contains 2/3 of a bag of positive electricity. Instead, they reflect how the relevant quantum fields are embedded in the gauge structure of the Standard Model. This is why physicists sometimes say that electric charge is the generator of electromagnetic symmetry, or more carefully, that the charge operator is associated with the generator of the unbroken electromagnetic $U1 symmetry. That sentence is technical, but its meaning is profound. The quantity we call charge is directly connected to one of the basic symmetries organizing the laws of particle physics. It is not simply a substance hiding inside matter. Yet this raises another question. If charge is a quantum property tied to symmetry, why does it appear to be conserved so perfectly? Why can particles be created or absorbed while the total electric charge refuses to disappear? The answer gives us one of the strongest clues that charge is a structural property rather than a material fluid. One of the most reliable rules in physics is conservation of electric charge. In every confirmed ordinary particle interaction, the total electric charge before the event matches the total charge afterward. Individual particles can disappear. New particles can appear. Energy can become matter. Matter can turn into radiation. But the electric charge accounting remains consistent? This is easy to see in electron and positron mutual conversion. An electron carries 1 unit of negative charge. A positron carries 1 unit of positive charge. Their total charge is 0. If they convert entirely into photons, the photons are electrically neutral, so the final charge is also 0. Nothing has violated conservation. Now run the logic in reverse. Under suitable conditions, energy can produce an electron and positron pair. A negatively charged particle and a positively charged particle have appeared, yet the total charge is still 0. This tells us something important. Pair creation is not like drawing positive and negative fluids from hidden reservoirs. The quantum fields allow a particle and antiparticle to appear together in a way that preserves the total conserved quantity. Another example appears in atomic beta conversion. At the particle level, a neutron can transform into a proton, an electron, and an antineutrino. The neutron begins with 0 total electric charge. The proton contributes +1 elementary unit. The electron contributes -1. The antineutrino contributes 0. The total remains 0. The identities of the particles have changed dramatically, but charge conservation survives. This suggests that electric charge belongs to a deeper accounting system than the identity of any specific particle. Electrons do not have to exist forever. Protons do not have to remain unchanged in every theoretical process. What must remain consistent is the total electromagnetic charge allowed by the interaction. The profound connection between conservation laws and symmetry was established through the mathematics associated with M.E. Noether. Very broadly, continuous symmetries can be linked to conserved quantities. The details of gauge theories require care, because local gauge transformations involve mathematical redundancy as well as physical structure, but the general relationship remains central to modern physics. Electromagnetic charge conservation is deeply connected to the $U1 structure of electromagnetism. This is very different from saying charge is conserved because the universe owns a fixed bucket of charged material that can never be eliminated. In modern field theory, conservation arises from the structure of the equations and the symmetries they obey. The theory does not need to imagine an indestructible substance passing secretly from one particle to another. That distinction becomes clearer when we consider particle transformations. A negatively charged muon can shift into an electron together with neutrinos. The muon disappears, but its negative electric charge is carried by the final charged particle. The identity changes while the total charge remains consistent. In weak interactions, quarks can also change type. Yet electric charge conservation continues to constrain the allowed process. Some reactions are possible. Others are forbidden because they would not preserve the necessary quantum numbers. Conservation therefore shapes what can happen in nature. It is not simply a pattern noticed afterward. The laws of the Standard Model are built to respect the unbroken electromagnetic gauge symmetry, and that structure enforces electric charge conservation. This is why a hypothetical reaction in which an isolated electron simply vanished into neutral photons would be a serious mathematical problem. The initial state would have negative electric charge, while the final state would have zero. That would violate the electromagnetic conservation law. The electron can transition only in a process where its charge is balanced by other charged participants. This fact gives us a powerful conceptual clue. If charge were merely one kind of microscopic material, its conservation might still be possible, but quantum physics does not need such a material picture to explain it. Charge behaves like a conserved generator associated with symmetry. That is a very different kind of explanation. It is one of the reasons modern physicists are comfortable saying that electric charge may be fundamental even if it is not made of smaller objects. The theory can tell us why the quantity must be conserved without telling us that it consists of some invisible substance. But another popular idea now appears. If electromagnetism is carried by photons, perhaps photons are the missing ingredients. Maybe charge is not a fluid, but a cloud of photons surrounding every charged particle. That possibility sounds reasonable at first, especially because quantum electrodynamics often describes interactions using photon exchange. But it does not survive careful examination. Photons are inseparable from electromagnetism, so it is easy to assume that electric charge must somehow be made from photons. After all, photons are the quantum particles associated with the electromagnetic field. Light is made of photons. Electromagnetic radiation is quantized into photons. In quantum electrodynamics, interactions between charged particles are often represented in calculations using photons. This seems to make the photon an obvious candidate for the hidden material behind charge. But there is a basic problem. Photons are electrically neutral. They do not carry positive or negative electric charge. That fact alone means we should not describe an electron's negative charge as a collection of ordinary photons packed around or inside it. The roles are different. A photon is a quantum excitation of the electromagnetic field. Electric charge is a property that determines how another quantum field couples to that electromagnetic field. The electron interacts with photons because the electron field is charged. The charge is not created by the photons. It is part of the rule that allows the interaction in the first place. In the mathematical description of quantum electrodynamics, the electron field and electromagnetic field are linked through an interaction term whose strength is determined by the electromagnetic coupling. Electric charge enters this interaction. In a Feynman diagram, an electron line may meet a photon line at a vertex. That diagram helps physicists calculate probabilities. It should not be treated as a literal picture of a tiny electron throwing miniature balls of light through space. Feynman diagrams organize terms in a quantum calculation. They are enormously useful, but they are not microscopic video recordings. This matters when people talk about virtual photons. A common explanation says that two charged particles attract or repel by exchanging virtual photons. As a shorthand within perturbative quantum field theory, that can be useful. But a virtual photon is not the same as an ordinary detectable photon flying between the particles. It is an internal element of a calculation. If we imagine it too literally, we start asking mechanical questions that do not reflect what the theory actually says. The electromagnetic field itself is the deeper object in the theory, and photons are its observable quantum excitations. Charge determines how charged matter fields participate in that interaction. The distinction becomes even clearer if we compare electromagnetism with the strong nuclear interaction. Gluons are the gauge bosons of the strong force. Unlike photons, gluons carry the kind of charge relevant to the strong interaction, called color charge. Because of this, gluons can interact directly with one another in ways that photons do not at the simplest level of electromagnetism. The difference comes from the mathematical structure of the gauge symmetries. Quantum chromodynamics is based on a non-abelian symmetry, while electromagnetic $1 is abelian. The details are technical, but the lesson is straightforward. Force carriers and charges are not the same thing. A gauge boson may or may not carry the type of charge associated with its own interaction, depending on the symmetry structure. In electromagnetism, the photon is neutral. There is another misunderstanding worth clearing up. A charged particle produces an electromagnetic field around it, so perhaps the field itself is the charge. Again, that is not quite right. Charge acts as a source in electromagnetic equations, while the electromagnetic field describes conditions throughout space and time. The field can carry energy and momentum. It can propagate as radiation. It can exist far from the charged particle that originally disturbed it. Charge and field are therefore intimately connected but conceptually distinct. In quantum theory, the relationship becomes even more subtle because a physically charged state cannot be completely separated from its long-range electromagnetic field. Yet that still does not mean the charge is a cloud of photons. The quantum field description is relational. The electron field has an electromagnetic quantum number. That quantum number determines its coupling. The electromagnetic field responds. Photons appear as quantized excitations of that field. This chain of ideas is more accurate than saying charge is made of photons. It also prevents circular reasoning. If we try to explain electric charge by saying the electron is surrounded by photons because it is charged, we would still have to explain why those photons are associated with the electron in the first place. The answer would again be that the electron field couples to electromagnetism because of its charge. So photons cannot explain the origin of charge. They participate in the interaction that charge makes possible. If we want to understand why particles have the particular charge values they do, we must look elsewhere. The next clue comes from the proton because unlike the electron, the proton really is composite. And inside the proton, electric charge reveals a remarkable fractional pattern. A proton carries 1 unit of positive electric charge, while a neutron carries 0 net charge. If protons and neutrons were elementary, we might simply list those values and move on. But they are not elementary. They contain quark and gluon structure. This allows us to see how the charge of a composite particle can arise from charges belonging to more fundamental constituents. In the simplest valence description, a proton contains 2 up quarks and 1 down quark. An up quark has electric charge plus 2/3 of the elementary charge. A down quark has minus 1/3. Add the 3 values and we get plus 1. 2/3 plus 2/3 minus 1/3 equals 1. A neutron contains 1 up quark and 2 down quarks. 2/3 minus 1/3 equals 0. This simple arithmetic explains why the proton has positive charge and the neutron is electrically neutral. The real internal structure of a proton or neutron is much more dynamic than 3 little quark balls sitting motionless inside a container. Quantum chromodynamics describes a complicated system of quarks, gluons, and quantum fluctuations. Even so, the total electric charge of the hadron remains well defined. The underlying charged quark fields combine to produce the observed net charge. This is an example where asking what the charge of an object is made from does have a meaningful answer. The proton's net charge can be understood through its charged constituents. But the explanation immediately creates a deeper question. Why does an up quark carry plus 2/3? Why does a down quark carry minus 1/3? We cannot currently answer those questions by opening the quarks and identifying smaller confirmed components. In the standard model, quarks are elementary fields. Their electric charges are part of their Electroweak quantum assignments. So the compositional explanation stops again. The proton's charge comes from quark charges, but the quark charges themselves are not presently known to come from smaller charged ingredients. This is where charge quantization becomes fascinating. Why do the charges of known particles fit together in such a regular pattern? The electron has -1. The positron has +1. Up-type quarks have +2/3. Down-type quarks have -1/3. Other generations repeat the same charge pattern. These values combine so that ordinary hadrons have familiar integer charges. They also allow protons and electrons to cancel each other in neutral atoms. That cancellation is extraordinarily important. Ordinary matter contains enormous numbers of protons and electrons. If their charge magnitudes were noticeably different, everyday objects could carry huge residual electric charges. Yet matter is observed to be neutral to extraordinary precision when proton and electron numbers balance. The standard model does not treat these values as unrelated accidents. They are connected to the Electroweak representation structure of quarks and leptons. Mathematical consistency also places restrictions on possible charge assignments. In particular, gauge anomalies must cancel. An anomaly is a quantum effect that can disrupt a symmetry that appeared valid classically. For a gauge theory to remain consistent, certain combinations of particle charges and representations must fit together correctly. In the standard model, quark and lepton contributions cooperate so that the dangerous gauge anomalies cancel. This is one clue that the charge pattern is not arbitrary. However, anomaly cancellation by itself does not always provide a unique, final explanation of every observed charge assignment without additional assumptions. Physicists therefore investigate deeper possibilities. Grand unified theories try to place quarks and leptons into larger symmetry groups so that apparently separate charges become parts of one unified structure. Another famous idea involves magnetic monopoles. Paul Dirac showed that if even one suitable magnetic monopole exists, quantum mechanics would require a relationship between electric and magnetic charges that naturally produces charge quantization. That is an elegant possibility, but no elementary magnetic monopole has been confirmed experimentally. There are also speculative models in which quarks and leptons have deeper constituents, but no such compositeness has been established. So fractional quark charge provides both an explanation and a mystery. It explains the charge of protons and neutrons while revealing that the deeper pattern itself still needs understanding. The values are not random within the standard model. They are tied to electroweak quantum numbers. To see how, we have to look at the equation that connects ordinary electric charge to the weak interaction. That equation shows that electromagnetism is not an isolated force sitting beside the weak force. At a deeper level, the two are intertwined. One of the most revealing facts about electric charge is that the standard model does not treat electromagnetism and the weak nuclear interaction as completely unrelated forces. They are combined within the electroweak theory. Before electroweak symmetry breaking, the relevant gauge structure contains an $SU2 part associated with weak isospin and a $U1 part associated with weak hypercharge. After the Higgs field settles into its non-zero vacuum state, the electroweak symmetry is reorganized. The W and Z bosons become massive, while the photon remains massless. The surviving unbroken symmetry is ordinary electromagnetism. Electric charge is associated with the generator of that remaining electromagnetic symmetry. In one common convention, the relationship can be written as $Q equals T_3 plus Y $. $Q represents electric charge. $T_3 represents the third component of weak isospin. $Y represents weak hypercharge. Some textbooks define hypercharge with a different normalization and therefore write the equation with a factor of 1/2, but the physical idea is the same. Electric charge is a particular combination of electroweak quantum numbers. This is a deeper statement than simply assigning -1 to the electron because experiments tell us it is negative. The electron belongs to a particular electroweak representation. Its weak isospin and hypercharge combine to produce its electric charge. The same framework explains why the electron neutrino is neutral even though it is partnered with the electron in a weak isospin doublet. Quark doublets follow the same logic. An up-type quark and down-type quark occupy related weak structures, yet their combinations of weak isospin and hypercharge produce electric charges of +2/3 and -1/3. This is where the pattern begins to look less arbitrary. Electric charge is embedded in a larger symmetry architecture. However, this does not mean the standard model completely explains why nature chose that architecture. The model tells us how the observed charges fit consistently into electroweak theory. It does not tell us with absolute finality why the universe uses precisely this gauge group, precisely these particle representations, and precisely these hypercharge assignments. That deeper origin remains open. This chapter also corrects a major misconception involving the Higgs field. People often hear that the Higgs gives particles mass and then assume the Higgs must also give them electric charge. That is not what the standard model says. Mass and electric charge are distinct properties. The Higgs mechanism breaks electroweak symmetry in a particular way. It gives mass to the W and Z bosons while leaving the photon massless. Fermion masses, including the electron's mass, arise through their Yukawa couplings to the Higgs field. But the electron's electric charge is not a quantity poured into it by the Higgs. Its charge follows from its electroweak quantum numbers and the surviving electromagnetic generator. A particle can be electrically neutral and still acquire mass through the Higgs mechanism. A particle can also be electrically charged and massive. The two properties must not be confused. This distinction matters because the question, what is charge made of, sometimes becomes mixed with the question, what gives particles their mass? Quantum physics answers those questions differently. Mass involves rest energy interactions, and, for elementary fermions and weak bosons, the Higgs mechanism. The mass of composite objects such as protons is dominated by quantum chromodynamic energy. Electric charge, by contrast, is tied to gauge symmetry and representation structure. The two concepts meet inside the same standard model but play different roles. The Electroweak framework also explains why the photon is special. The photon corresponds to the unbroken electromagnetic gauge symmetry, which is why it remains massless in the standard model. The W and Z belong to broken directions of the Electroweak symmetry and become massive. This survival of an unbroken U1 is directly connected to the continued conservation of electric charge. So by following the charge question, we have uncovered several layers. At the everyday level, charge explains attraction, repulsion, sparks, and currents. At the quantum level, it determines coupling to the electromagnetic field. At the Electroweak level, it emerges as the generator of a surviving symmetry after electroweak breaking. None of those layers requires charge to be a microscopic substance. Instead, they increasingly describe it as a structural feature of the theory. But there is still another complication. If the electron's charge is fixed by its quantum identity, why do physicists say the electromagnetic coupling becomes stronger at higher energies? Does the amount of charge actually change when we probe smaller distances? The answer involves the quantum vacuum and one of the most subtle ideas in quantum field theory, renormalization. The word symmetry usually brings to mind shapes. A butterfly has approximate left-right symmetry. A circle looks the same after rotation. A crystal repeats a pattern in space. But the symmetries that organize particle physics are often not visible geometric symmetries. They act in abstract mathematical spaces associated with quantum fields. Electromagnetic U1 symmetry is one of these internal symmetries. Its connection to electric charge is so deep that understanding charge without at least a basic idea of gauge symmetry is almost impossible. Begin with a quantum matter field such as the electron field. Its mathematical description contains a complex phase. If we shift that phase everywhere by the same amount, measurable physics remains unchanged. This type of transformation is associated with a global U1 symmetry. Now make the phase choice vary from one place to another. To preserve the structure of the theory under these local transformations, we introduce a gauge field. In electromagnetism, this gauge field is the electromagnetic potential, whose quantum excitations are photons. The requirement of local gauge structure therefore naturally connects charged matter to electromagnetism. The amount and sign of charge determine how the matter field transforms. This sounds almost magical when stated quickly, so it is important not to exaggerate what gauge symmetry means. It is not accurate to imagine that nature physically rotates an invisible internal wheel and thereby creates electricity. Gauge transformations often relate different mathematical descriptions of the same physical situation. In that sense, gauge symmetry contains redundancy in our description. Yet the requirement that the theory possess the appropriate gauge structure places powerful constraints on the possible interactions. It tells us how fields can couple. It helps determine the form of the electromagnetic equations. It is deeply linked to the existence of a massless photon and to electric charge conservation. So although the gauge transformation itself is not a visible motion like turning a snowflake, the structure it represents has measurable consequences. This is why physicists do not treat symmetry as decorative mathematics added after experiments. Symmetry is one of the central organizing principles used to construct modern particle theories. The standard model is built around gauge symmetries. The electromagnetic, weak, and strong interactions are described through different gauge structures. Their differences explain why their force carriers behave differently and why their charges have different properties. Electric charge belongs specifically to the unbroken electromagnetic $1. The strong interaction has color charge and in $SU $3 gauge symmetry. The weak and electromagnetic interactions emerge from the electroweak $SU $2 and $1 framework. Once we see this larger pattern, electric charge begins to look like one example of a broader principle. Fundamental interactions are organized by symmetries, and particles are classified by how their fields transform under those symmetries. The word charge can even be generalized. In quantum field theory, different gauge interactions have corresponding charges or quantum numbers. Electric charge is simply the one associated with electromagnetism. Color charge governs the strong interaction. Weak quantum numbers determine participation in weak processes. These charges are not necessarily made of physical substances. They are labels describing representation and interaction structure. This does not make them less real. A color charge determines whether a particle participates in the strong interaction. Electric charge determines whether and how it participates in electromagnetism. The physical consequences are measurable in scattering experiments, particle transitions, detector tracks, atomic spectra, and countless other observations. Another important number appears here, the fine structure constant. This dimensionless quantity measures the strength of electromagnetic interaction. At low energies, its value is close to 1 divided by 137. Physicists have long been fascinated by this number because the Standard Model does not derive its low-energy value from a deeper principle. It is measured. The theory then tells us how the effective coupling changes with energy. This highlights a useful distinction. The existence and charge assignment of a field are one thing. The numerical strength of the electromagnetic coupling is another. Both are parts of the theory, but they answer different questions. The electron has a definite electromagnetic charge quantum number. The electromagnetic interaction also has a coupling strength. When the two combine, we obtain the observable interaction strength. This layered structure is another reason simplistic statements such as charge is just energy or charge is just photons fail. Energy, fields, quantum numbers, and couplings are related but distinct concepts. Symmetry tells us how the pieces fit together. Yet even symmetry is not necessarily the final answer. We can always ask why nature has this symmetry rather than another one. That question remains open. Before we reach that frontier, however, we need to explore a strange effect that can make electric charge appear different depending on how closely we look. The quantum vacuum itself changes the effective strength of electromagnetism. Empty space sounds simple. Remove all matter, remove all radiation, and nothing should remain. Quantum field theory gives us a more subtle picture. The vacuum is not ordinary empty nothingness. It is the lowest energy state of quantum fields. Those fields still exist, and their quantum behavior can affect physical processes. Recent high-precision experiments, like Fermilab's muon G2, continue to confirm just how intensely these vacuum interactions dictate physics at the subatomic scale. One of the clearest examples appears in quantum electrodynamics through an effect called vacuum polarization. Suppose we probe the electromagnetic interaction of a charged particle. The quantum fields of electrically charged particles contribute corrections to the propagation of the electromagnetic field. In perturbative calculations, these effects are represented by loops involving charged fields. The result is that the effective electromagnetic coupling depends on the energy or momentum scale of the experiment. Popular explanations often picture this as a charged particle surrounded by a cloud of virtual particle-antiparticle pairs. The vacuum becomes polarized, with opposite charges tending to screen the central charge when viewed from far away. If we probe at shorter distances, we penetrate more of this screening and see a slightly stronger effective interaction. This picture can help intuition, but it should not be taken literally. Virtual particles are not tiny objects that can be photographed orbiting an electron. They are components of a quantum calculation. The rigorous statement is that quantum loop corrections modify the relationship between the electromagnetic coupling measured at different scales. This leads to what physicists call the running of the electromagnetic coupling. At low energy, the fine structure constant is close to 1 divided by 137. At higher energy, the effective electromagnetic interaction becomes somewhat stronger. Now we face an apparent contradiction. Earlier we said every electron has the same fixed electric charge. If the interaction changes with energy, does the electron become more charged when we look more closely? The answer is no, provided we distinguish two different meanings. The electron's charge quantum number remains fixed. It does not change from -1 to -0.9 or -1.1 as the collision energy increases. The electron remains the same kind of field excitation and transforms under electromagnetic symmetry in the same way. What runs is the effective coupling strength after quantum corrections are taken into account. Physicists sometimes use language such as running charge as shorthand, but that should not be imagined as a literal amount of charged substance swelling or shrinking inside the electron. The effect arises because quantum fields influence the way the electromagnetic interaction is observed at different scales. This is one of the reasons renormalization is essential in quantum field theory. Early calculations in quantum electrodynamics produced infinities that seemed mathematically unworkable. The modern renormalization framework shows how the parameters appearing in the theory must be related to measurements made at specific scales. Instead of treating the infinities as evidence that the entire theory is meaningless, physicists learn to organize the scale dependence systematically. The result is one of the most precise predictive frameworks ever developed. Renormalization is sometimes described unfairly as a trick for hiding infinities. A better view is that it reveals how a quantum field theory changes its effective description as we move between energy scales. The values of couplings are not isolated numbers detached from the scale of observation. Quantum fluctuations influence them. This does not explain the existence of electric charge, however. That distinction is crucial. Vacuum polarization modifies how the electromagnetic interaction appears. It cannot be the ultimate source of the electron's charge because the calculation already assumes that charged fields exist and couple to electromagnetism. In other words, the theory needs electric charge before it can calculate how vacuum polarization dresses that charge. Saying the vacuum creates the electron's basic charge would therefore be circular. The vacuum changes the observed effective coupling. It does not explain why the electron field carries the electromagnetic quantum number in the first place. This correction is important because internet explanations sometimes say that an electron's charge comes from a cloud of virtual particles around it. That is not what established quantum electrodynamics says. The electron's charge assignment is fundamental within the theory. Quantum effects modify the relationship between bare parameters, renormalized parameters, and measurable interactions. The distinction can be subtle, but it protects us from turning mathematical techniques into fictional microscopic stories. By now, the pattern is consistent. Each time we try to turn charge into a material substance, quantum field theory redirects us toward relationships. Charge determines coupling. Symmetry organizes the coupling. The vacuum modifies the effective strength. None of these effects reveals a smaller physical grain from which electric charge is built. There is still one more powerful clue. Antimatter shows us that positive and negative charge are not two separate materials but opposite values of the same underlying quantum property. The positron looks like the perfect mirror partner of the electron. It has the same mass as the electron. It has the same amount of spin. But its electric charge has the opposite sign. The electron carries -1 elementary unit. The positron carries +1. This relationship is not accidental. The positron is the electron's antiparticle, and in relativistic quantum field theory, particles and antiparticles arise naturally from the structure of quantum fields. The existence of the positron immediately tells us that positive and negative electric charge are not simply two different chemical substances. A positron is not an electron that has been filled with positive fluid instead of negative fluid. It is a distinct quantum excitation associated with the same underlying field structure and carrying the opposite electromagnetic quantum number. This becomes visible in particle detectors. When an electron and positron travel through the same magnetic field with similar momenta, their trajectories bend in opposite directions because their electric charges have opposite signs. That curvature gives physicists a direct way to determine charge sign. The charge therefore has measurable consequences, even though it is not a material ingredient. Antimatter also demonstrates charge conservation beautifully. Bring an electron and positron together under suitable conditions and they can mutually convert into pure energy. Their particles disappear, often producing photons. The electrons -1 charge and the positrons +1 charge add to 0 before the interaction. The photons carry 0 electric charge afterward. Total charge remains 0. The particles are gone, but the conservation law is satisfied. Pair creation shows the reverse. Energy can generate an electron and positron together. It may look as though electric charge has appeared from nowhere, but the positive and negative contributions cancel exactly. Net charge remains unchanged. These processes would be very strange if charge were a substance permanently attached to a particle. Quantum field theory handles them naturally because particle number and electric charge are different concepts. The number of electrons can change. The number of positrons can change. The conserved electromagnetic charge tracks the total state. There is also an old phrase saying that a positron can be viewed as an electron moving backward in time. This idea has mathematical usefulness in certain ways of interpreting Feynman diagrams, but it should not be treated as literal footage of an electron physically reversing through time. The cleaner statement is that electrons and positrons are particle and antiparticle excitations carrying opposite electric charges. Antimatter also helps us avoid confusing the proton with the positron. Both have positive charge, but they are completely different particles. The positron is elementary within the Standard Model and is the electron's antiparticle. The proton is a composite hadron made from quark and gluon structure. Its mass is about 2,000 times greater than the electrons, and it participates in the strong interaction. Yet the magnitude of the proton's charge matches the magnitude of the electron's charge with extraordinary precision. This matching is essential for neutral matter. A hydrogen atom combines one proton with one electron, and their opposite charges cancel. Larger atoms contain equal numbers of protons and electrons when electrically neutral. The fact that particles with such different structures carry exactly opposite net charges is one of the reasons physicists suspect a deeper organizing principle may exist. Within the Standard Model, the charge pattern is linked through Electroweak quantum numbers and anomaly cancellation. Beyond the Standard Model, grand unified theories attempt to explain the relationship by placing quarks and leptons inside larger symmetry structures. Magnetic monopoles offer another route. Dirac showed that if magnetic monopoles exist, quantum mechanics can force electric charge into quantized units. That would provide a beautiful explanation for why charge does not seem to take arbitrary values. But neither grand unification nor elementary magnetic monopoles have been experimentally confirmed as the final explanation. Antimatter therefore teaches us something definite while leaving something deeper unresolved. We know what opposite charge means operationally. It means opposite transformation and response under electromagnetism. We know that particle and antiparticle charges cancel. We know that charge conservation survives creation and mutual dissolution. What we do not yet know is why the universe chose the entire observed charge pattern in the first place. And this brings us to the final chapter. After all the fields, photons, symmetries, quarks, antiparticles, and vacuum effects, can we finally say what charge is made of? We can now return to the question we started with. What is electric charge made of according to quantum physics? For an elementary particle such as the electron, the best supported answer is that electric charge is not currently known to be made of anything smaller. In the Standard Model, it is a fundamental quantum property associated with electromagnetic gauge symmetry. It tells us how a quantum field transforms under the electromagnetic $1 symmetry and how that field couples to the electromagnetic field. This answer is very different from the picture most people expect. We usually understand something by breaking it into components. Molecules are made of atoms. Atomic nuclei contain protons and neutrons. Protons and neutrons have quark and gluon structure. At each level, a larger object can be explained using smaller ingredients. Electric charge does not currently fit that chain at the level of elementary particles. For a proton, we can explain its net positive charge using the electric charges of its underlying quark fields. For an atom, we can explain net charge by counting protons and electrons. For a metal object, we can explain charging by the redistribution of electrons. But for the electron itself, there is no confirmed deeper constituent whose charges add together to produce -1. The Standard Model treats that charge assignment as fundamental. This does not mean physics has no explanation at all. We understand charge structurally. We know it is connected to an unbroken $1 electromagnetic symmetry. We know it is related to Electroweak quantum numbers. We know it controls coupling to photons. We know the total electric charge is conserved. We know quantum corrections cause the effective electromagnetic interaction to run with energy. We know antiparticles carry opposite charges. We know quark charges combine into the net charges of composite hadrons. We can calculate these effects with extraordinary precision. What we do not have is a confirmed deeper theory explaining why the complete charge pattern exists exactly as observed. Why does the electron carry -1? Why do quarks carry +2/3 and -1/3? Why do quark and lepton charges fit together so that a proton has exactly the opposite net charge from an electron? Why is the electromagnetic coupling strength what it is? Why does nature use this particular gauge structure? These are questions at the frontier rather than failures of basic understanding. Several ideas try to answer them. Grand unified theories suggest that the standard model gauge groups may be parts of a larger symmetry at extremely high energies. In such theories, quarks and leptons can be grouped into common representations, and their charge relationships may emerge naturally rather than being inserted separately. Magnetic monopoles provide another intriguing possibility because their existence could enforce charge quantization through the Dirac condition. Compositeness models imagine that quarks and leptons may contain deeper constituents, allowing familiar charges to emerge from a lower layer. Other approaches explore whether properties we call fundamental could arise from an even deeper quantum structure. But none of these possibilities has yet been experimentally established as the final explanation of electric charge. This distinction between what is known and what is possible is essential. Science should not fill a gap in evidence with a dramatic story. We cannot say that charge is definitely made of preons, strings, virtual particles, Higgs energy, or some undiscovered fluid. Current evidence does not establish those claims. We can only say that the standard model describes electric charge as fundamental at the level of its elementary fields. There is also a philosophical lesson here. Not every explanation has to be a story about smaller pieces. Imagine asking what a mathematical symmetry is made of. The question may be using the wrong category. A deeper theory could someday show that electric charge is unavoidable once certain principles are imposed. If that happened, charge would be explained without being decomposed. The answer would be closer to nature must have this structure, then charge consists of these smaller particles. That possibility is difficult to picture because human intuition evolved around physical objects, not quantum fields. We understand tables by taking them apart. We understand machines by opening them. Fundamental physics may eventually require a different kind of understanding. The deepest layer may consist not of smaller objects but of relationships, symmetries, and rules determining which quantum states can exist. Electric charge may be one of those rules. Or it may eventually turn out to be emergent from something still deeper. We do not yet know. What we do know is enough to answer the original question carefully. Charge is not known to be a substance inside particles. It is not made of photons. It is not simply the Higgs field. It is not the same thing as energy. For elementary particles in the standard model, electric charge is a fundamental quantum property tied to electromagnetic symmetry and interaction. That is where our experimentally established understanding currently ends. Beyond that boundary lies one of the most interesting questions a future theory of fundamental physics may have to answer. A spark from your finger looks simple, but follow its physics deeply enough and the idea of charge changes completely. It stops looking like an invisible substance and starts looking like part of the architecture of quantum theory. Charge tells a quantum field how it participates in electromagnetism. It is connected to symmetry, conservation, photons, quark structure, and the Electroweak theory. Yet the deepest question remains open. Why does nature contain this exact pattern of electric charges at all? Maybe a future theory will reveal another layer underneath. Maybe charge will turn out to be fundamental in a way that cannot be reduced to smaller pieces. For now, quantum physics gives us an answer that is stranger than a hidden particle. Electric charge is not known to be made of anything. It is a rule written into the quantum structure of nature.